In this video, we want to solve this system of equations. And it's worth noting that this is a system of nonlinear equations. It turns out that this first equation, y equals 4 to the x plus 3 power, this is actually an exponential equation. So this is a system of nonlinear equations. However, we still have the same methods of solving. We can choose substitution or we can choose elimination. So for this problem, I'm going to go ahead and choose substitution since in the top equation I already have y isolated. Y is already by itself. So I'm going to go ahead and take the 4 raised to the x plus 3 power and substitute it into my second equation in place of y. So that's going to give me 4 raised to the x plus 3 power minus 2 raised to the x squared plus 3x power is equal to 0. And then I'm going to add the 2 to the x squared plus 3x power to the other side so that I have these two exponential expressions, one on each side of the equal sign. Now let's talk about the base on the left. So the left side has a base of 4 and the right side has a base of 2. And we know if we can get the bases to be the same, then the exponents are going to be equal. So we can rewrite 4 as 2 squared. Then that will be a base of 2. So 4 is 2 squared, and then that is still being raised to the x plus 3 power, and that's equal to 2 raised to the x squared plus 3x power. So on the left-hand side, we have a power raised to a power. And so if you remember your rules with exponents or properties of exponents, you multiply your exponents when you have a power raised to a power. So we'll multiply our exponents here, which means we'll be multiplying the 2 times the x plus 3. So we'll have 2 raised to the 2 times x plus 3 power is equal to 2 raised to the x squared plus 3x power. Then I'll go ahead and distribute my exponent. So I'll have 2 raised to the 2x plus 6 power is equal to 2 raised to the x squared plus 3x power. And then notice I've reached the point where the bases are the same. Therefore, the exponents can be set equal to one another. And that's using the uniqueness property. We studied the uniqueness property when we first were introduced to exponential equations. So 2x plus 6 is equal to x squared plus 3x. And now we have a totally different type of equation here. This is not an exponential equation anymore. Now we have a quadratic equation. So we'll review how to solve quadratic equations. We know it's quadratic because it's degree 2. So I'm going to choose to leave everything on the right-hand side and then subtract the 2x and subtract the 6, so that way we're setting this equal to 0. So if I subtract 2x from 3x, that's going to just be a positive 1x or positive x, and then we'll subtract 6. And then we always are going to try to factor first when we're solving quadratic equations. And if it doesn't factor, then we'll go to quadratic formula. So I'm looking for two numbers that will multiply to give me negative 6. So two numbers that multiply to give us negative 6, but those same two numbers need to add to give us the positive 1, which is the coefficient of the x term. So it looks like we would be able to use some combination of 3 and 2, but one of them will need to be negative. And if it is a positive 3 and a negative 2, that will multiply to give us negative 6, and that will add to give us positive 1. So we have 0 equals x plus 3 times x minus 2. So we'll set each of these factors equal to 0 and solve these two linear equations, which gives us x is equal to negative 3 and x is equal to positive 2. Now remember, if we go back to the original problem that we were given, the original problem was a system of equations. And a system means we have two equations with the same unknowns, so we're really looking for the intersection point, or points. We're looking for the points where these two curves intersect. So finding the x value is not sufficient. I don't want you to think you're done here at the bottom now that we found x equals -3 and x equals +2, but rather we need to take these x values and we need to substitute them back into one of the original two equations. Remember, it doesn't matter which equation you substitute it back into because we're going to look for the points where the two curves intersect. So the points will be on both curves. So I always just encourage you to plug them back into whichever curve you think is going to be easiest for you. And in this case, I'm going to come back here to the top curve, y equals 4 raised to the x plus 3 power, since it already had y by itself. So let me start with x equals -3. And if I substitute that back in, y equals 4 raised to the -3 plus 3 power. So that's going to be y equals 4 to the 0 power, and 4 to the 0 power will be 1. So when x was equal to -3, y was equal to 1. So we'll write our answer as an ordered pair. So that's the intersection point -3, +1. That will be one of our intersections. And then we'll do the same thing for x is equal to 2. So y equals 4 raised to the 2 plus 3 power, which is going to be 4 to the 5th power. It's okay for you to go ahead and grab your calculator. I don't expect you to know 4 to the 5th power on your own. And that looks to be 1024. So when x was equal to +2, we ended up with a y value of 1024, and that means the intersection is 2, 1024. So we ended up with two intersection points. And again, just to recap, the actual answers then would be these two intersection points that I've got outlined or highlighted here in green. -3, 1 is one of our solutions, and 2, 1024 is our second solution.